Dear colleagues, dear guests, it's my great pleasure to welcome you to this part of the conference and present the Paul Ehrenfest Best Paper Award for Quantum Foundations, an award that honors significant contributions to the foundations of quantum mechanics. The Ehrenfest Award conferred annually to the authors of the work published within the past 5 years that has made a considerable impact on the field. Both theoretical and experimental works are eligible for this award, and our aim is to raise awareness and importance of quantum foundations while recognizing the vital contributions made by researchers in this area. The prize is named after Paul Ehrenfest, a brilliant physicist of the early 20th century, known for his profound contributions to quantum theory, statistical mechanics, and gravitation. So without further delay, with some delay, so I'm very proud to introduce the winning trio of papers for 2023, a no-go theorem for observer-independent facts by Brukner, quantum theory cannot be consistently described by the use of itself by Frauchiger and Renner, and a strong no-go theorem on the Wigner's friend paradox by Bong, Utreras-Alarcón, Ghafari, Liang, Tischler, Cavalcanti, Pryde, and Wiseman. So the members of the selection committee of the Paul Ehrenfest Award for 2023 year were Borivoje Dakić from the University of Vienna and Ikoki, that's me. Philip Goyal from the State University of New York at Albany, Philip is also here. Lucien Hardy from the Perimeter Institute in Waterloo, Canada. Marcin Pawlowski from the University of Gdańsk, Poland. And Urvashi Sinha from the Rama Research Institute in Bangalore, India. So the committee has concluded the following. In these papers, the authors extend Wigner's famous thought experiment by combining it with aspects of Bell setup, thereby constructing a variety of closely related no-go theorems. These theorems challenge the applicability of quantum mechanics to arbitrary physical systems, including macroscopic objects and observers, paid with various assumptions such as the absoluteness of measurement outcome or certain locality assumptions, some of which are weaker than those in Bell's theorem or Cohen-Specken theorem. As a result, these theorems provide new challenges for the interpretation of quantum theory, forcing us to make some hard choices in our conception of quantum reality. So dear Časlav, dear Renato, dear Eric, congratulations to you and your co-workers. I kindly invite you for the award certificate, and Flavio will take some pictures. Renato? Okay, so now we will proceed with a rather short presentations by all three works. So I will be a chairman. I kindly ask you to keep your questions for the end. So after all three speakers have their presentations. So Časlav, you will start, please.
Okay. So, good afternoon, everybody. Let me start by thanking the award committee headed by Bori, and Philip is here as well, and all other members for selecting the 3 papers for the award Paul Ehrenfest 2023. I also want to extend my thanks to 2 further persons who nominated us for this award, David Schmidt and Matt Leifer. I don't know where you are. Matt is there, and David is over there. Thanks. That's a great pleasure and also an honor to share this prize with the colleagues of mine, with Eric, Renato, and also co-authors of the 2 papers. So I decided to put the title, What Happens, for the talk today. And so let me start with an experiment. And that is like, I will hit this desk, I hit even harder, and you hear this. And we can maybe agree that this is an event, that this is something which really happens. Really happens because you have done it in the past, you know how it feels. And we shared the sound, and we have immediate experience of that. So maybe there are different approaches to what an event could be. Maybe people who are, from an interpretational point of view, a little bit more on the realistic side will say, well, this is not the elementary event. Maybe it's composed of many other elementary events, but no doubt it's a composite event, and it is an event. It's immediate experience. Those who are more on the Copenhagen side, maybe they will say, oh, this is the thing that we start with. That's the elementary Borean phenomenon, and that's his event. So in entire my talk, I will talk about those events, and I hope that we have no disagreement that they are happenings. Okay. Now, today in the morning, Anton Zeilinger said that he has a very strong belief that no matter how complex, how large or heavy objects are, they will eventually be quantum mechanical, and we will eventually be able to show quantumness, given that we have enough funding for the experiments. Now, these 2 statements are quite distinct to each other. And what I want to show today, that if we believe in what Anton Zeilinger believes, we should maybe have an element to doubt that these events we can actually share among us. And even if I do it harder, and I start to feel pain, you might hear these events, but not only that you will not share the pain, which you do not anyway, even just to imagine at the same time, from your perspective, that I share pain, that I feel the pain, that it hurts, combined with any events that you share, are not compatible. We cannot combine them in any logical framework. We cannot assign truth value to the questions whether I feel pain and you do something else. Okay, that's a long path towards that. And these seems to be quite disentangled statements. Now, the way how to arrive at this conclusion is to combine 2 elementary experiments in quantum mechanics, one of them being Gedanken experiment, the other one used to be a Gedanken experiment, it's now a real experiment. And this is Wigner's friend experiment and Bell's experiment. One done by Wigner, thought experiment, thought through, one 1961, the other in 1964. Now, what I want to tell you a little bit at the beginning is my personal path towards combining these 2 puzzles and towards the statement that I made at the beginning. So somewhere in November 2013, I was at the workshop in the beautiful place Traunkirchen, Austria. Chris Fuchs knows the place very well. I've been discussing with Richard Hillier a lot about the meaning of the Wigner's friend. And somewhere at the end of this workshop, I had some vague impression that the Wigner and Wigner's friend should have incompatible experiences, or should something was not fitting that together. Not only in a sense that there is ambiguity in assigning the state that they do, but something more deeper. And this idea crystallized very well so that I could present this in June 2014 at the Vienna conference. This was 10 years ago for the 50 years of Bell's theorem. But it was very speculative, and luckily I was forced to write down a proceeding for this conference, where you usually write the things that are very speculative and you do not dare to write elsewhere. And so I wrote this thing and submitted on archive in 2015, which was eventually published in 2017 in the proceedings. Now, it was not a surprise for me that there was no reaction. But seemingly, and almost no citations as well, but seemingly one group at that time read this paper, and I had one citation then coming in 2018, and that was Frauchiger and Renner paper, where they cited me. And this paper got quite attention. There was a huge echo in quantum foundation community, but somehow my 2015 papers was still not read. And then I write another paper, which was rewriting the argument once more. Okay, you choose different words, you try to be more precise, that was 2018. So what I want to tell you, especially for young people, if you think that some idea is right, say it loud, say it many times. And just because of this 2018, I could got this award, because it was for the last 5 years. Okay, what is the path to the award? So, I said there are two experiments that are involved in this argument. One is Bell's theorem. There are many different readings of Bell's theorem. The one that I like is that the theorem assumes that the measurement you did not do would have had a definite outcome. So it has a flavor of counterfactual reasoning. And hidden variables are exactly introduced to determine joint probabilities, both for actual but also counterfactual outcomes. And now, the reaction to the relational Bell inequalities could be that you should not do that. And Asher Perez nicely put it in the title of his work, unperformed experiments have no results. And I found a peace with this. And also I have some work with Anton that he mentioned, in which we claim that quantum systems contain finite information, and so they can answer only one question. They cannot have prepared answers to many experimental questions, which was somehow fitting in this understanding of Bell's theory. Okay, that's one part of the puzzle. The another experiment that comes here into play is Wigner's thought experiment in 1961, where he considers two observers, one of them being, let's say, inside a lab or box, that's the friend, performing some experiment on spin, and having an outcome, getting an outcome, an immediate experience, just like that. It is a click of the detector. Now, upon observation, this observer will update the knowledge and will have either one or the other state. And this is very important information for any future experiment to be performed in the lab. On the other hand, if we think that this is really a totally sealed laboratory, one could imagine that there is an external observer for whom there was no measurement, And therefore, this observer could still think about this measurement as just an interaction between two quantum systems for which he will write down a state. And this state is this entangled state because he doesn't know what has happened inside. Now, there was a very important variant of this experiment done by Dakić in 1985. I don't even know if you have seen the change. The change from this to that is that he adds a measurement. And now, it's not only a description that is entangled, description according to Wigner, this entangled state, it's more than that. Wigner can actually verify, confirm that from his point of view, this is an entangled state. And now, there was one element more in his paper. He said, not only that, the friend can communicate to the Wigner by saying, for example, dear Wigner, I have performed a measurement and obtained a definite outcome. So at that point, Wigner could think like, I have seen my outcome, and there is some evidence that there is a definite outcome inside. Is it not enough? Is it not enough evidences that assume that two outcomes coexist? And so by simply acknowledging that the friend preserves her outcome in the same way as he does, Wigner is almost compelled to introduce a hidden variable to determine the joint probability for both her and his outcome. So it's not only anymore about counterfactual reasoning. Why should I take care about counterfactual reasoning? There is an observation of both outcomes, admittedly by different observers. And that's exactly the moment where you can fall into the hidden variable trap. Namely, you can start to think that these joint probabilities exist. And you can assign, for example, some value to friend's outcome and some value to Wigner's outcome and say, well, there is enough evidences. I put and define the joint probability for these two. And this is a simple exercise, and let's keep this extremely simple and think just that the outcomes are binary outcomes, that you have +1 or -1. And now you can think about, to denote the measurement result of Wigner in this entangled basis as X. This is the second digit in this binary pair, and the Z to be a measurement that friends keep measuring. And then you can think, okay, I assume that this exists, but whenever I want to say what really Wigner observes, I don't have, from the Wigner's point of view, I don't have access to both of them, so I would just assume that what Wigner observes is the marginal probability of this joint probability. That's one understanding of his entanglement measurement. But then he can maybe do something else. Maybe Wigner can open the lab and so to say ask the friend what she observes, or look at the same measurement device as Wigner does. As the friend does. And then this, what now Wigner will see, does not necessarily need to be just the margin of these joint probabilities, because by opening this box you can maybe do something destructively on the result that there was before opening the box. So, in a sense, opening the box may disturb what the friend has seen. Now, these elements put together bring us to the Wigner's Bell scenario that was introduced in this 2015 paper, and in which we have two Wigners and two friends, and let's call friends Charlie and Debbie, and Alice and Bob are Wigners on two sides. And then, by the same argument, in which, for example, friends can send out the messages claiming that they see definite outcome all the time, the two Wigners could come up with the idea that there must be a joint probability for all four outcomes. Hello? Two of them for Wigner and two of them for friend. Now, I want to make a next step towards the Bell's experiment. Namely, I want to define what two Wigners, Alice and Bob, can measure. And I say they can either ask the friend which results she observes by opening the boxes, or they can measure still the laboratory in entangled basis and introduce corresponding observables in quantum mechanical formalism. And now you have another element of the whole theorem, and that's locality. You say, okay, sure, asking the friend about measurement or opening the box can indeed disturb the result that was there before, but we assume that this disturbance is local. So asking the friend measurement can disturb only what the local friend has seen in the box, and nothing what is distant from this box, distant from this laboratory. This assumption and assumption about existence of this joint probability lead us to the Bell-type inequalities, which we know, if we believe in quantum mechanical formalism, we can violate. And so we can conclude that no opening of a box that disturbs only what the local friend has seen in the lab can explain the Bell inequality violation. And that's the end of 2015 paper. Not fully, technically. Now the question is what we can learn from that. But before I go into what we can learn from that, and what is written in these 2015 papers, I want also to say that there is a disadvantage or a loophole of the argument. And the thing is related with the fact that in some cases, in my theorem, I still assume that the results of experiments not carried out exist. And these are those cases when we open the box, let's say Alice opened the box, can disturb the Charlie's result, but in this argument, I still assume that there is existence of the Alice measurement, although she had decided, of the first entangling measurement, although she decided to open the box. So I see my theorem somewhere in between Bell's theorem and local friendliness, that you will hear later on, because this theorem gives more substance in the assumption why we should assume that there is these outcomes over there, at least in some subset of the cases. And there is this one setting in which all four outcomes are there, so you can think about all other measurements as some kind of a coarse graining of this small, fine-grained set of all four measurements. But however, there is this disadvantage. And this disadvantage was then turned into a new theorem, a wonderful theorem, which is called local friendliness, and Eric will talk next about that. But at that moment, I want to say that when local friendliness appeared, I was just amazed, because I thought that you can't go beyond Bell inequalities, that this kind of this kind of disadvantage will be there, and was not convinced that you can overcome that, and that I was disproved. But I was not unhappy about that. So what you see here is a cover page of Süddeutsche, a newspaper in Germany. It says, "Unhappy Austria, a study criticized local friendliness." And it says also that the Austrians are the only nation that is more grumpy than Kuwait. You can think about this as a recommendation for our elections that are coming now on Sunday. So, what happens? That was the question at the very beginning. There are several possible paths. One possible path is a measurement is a measurement for everyone. It makes no sense to consider the Franz apparatus as a part of Wigner's quantum system. In our papers, we call this non-universality of quantum mechanics, but I'm not sure that people who support this idea would like this name. And the prominent supporter of this idea is Wigner's Wigner's enemy. I think you see also the name of the badge. It's a Marek Żukowski badge. When I saw this, it came immediately to my mind. An enemy of your enemy is your friend. But since I consider Wigner and his friend not so great friend as Marek, I left this option of reply. So indeed, Marek Żukowski, Philippe Grangier, also I would call traditional Copenhagen, have this view that there is nothing after the measurement, that measurement is actually for everyone. One possible way to understand when I think about this as a realistic option is what Marek actually told in his talk, that the resources that are required to perform this experiment maybe exceed the resources that are available in the whole universe. So why should we care about that? That, unfortunately, has to be proven. And it could be that in this proof we overcome the possibility to do something with the finite resources. And at the end, the possible answer towards this exit is that there are collapse models, and I've never thought that Marek will be in the group of people who support collapse models. That's a moral. You do not, but from that point of view, you are not far away. Okay, what would be the other option? Other option would be that opening a box has a non-local effect on what the distant friend of Wigner sees. It's some kind of non-locality, and Bohmian mechanics or some other non-local theories go this way. And it's very much related to Nicolas Gisin's question mark, signaling question mark title. And we in the group, Veronica and myself, play around with that. And we thought about the friend, or modeling the friend, as having two different parts of memory. One in which the friend stores the result, and the other type of memory in which we only remember or notice if the first memory has changed or not. So the first memory could be deleted and replaced with something else, but this second part of memory can notice this. Now, if you have such a friend, and you put it in the Wigner's friend scenario, what we showed here, and people who are familiar with non-locality will see this immediately, you could signal. So you can think about this as intellectual training, saying that if you think that there is no signaling, you should not have this second part of the memory. But I want to give some seriousness to this idea by the mere fact that we can think about these experiments in somewhat operational way. Now I come to Anton's talk and his question mark, reality question mark. That's where I am closest, but I'm open. So the idea is that the facts are relative. They are relative to the context, observer, or Cavalcanti's expression, bubble. So the assumption of the existence of the joint probability was wrong from the very start. That could be an answer, and cubism, I think, will assign to that for different maybe reasons. Relational quantum mechanics, with which I have many other problems, but not this one. Or something like Neo-Copenhagen approach. And here I read the conclusion of my 2015 papers. It says, well, the view that holds the coexistence of the facts of the world, common both for Wigner and his friend, runs into the problem of hidden variable program. The solution lies in understanding the facts can only exist relative to the observer. Now, is it strange? Well, there is some analogy with the special relativity that we put forward, again, I think all three of us. Namely, in special relativity, every inertial observer claims that her or his clock ticks faster than that of a moving partner. Taken together, the claims would lead to some kind of inconsistency under inverted commas. However, The statements have only meaning with respect to the specific observer-dependent measurement procedure defining simultaneity. And that was put forward by Sudbury, if I'm not mistaken. Now, similarly, the outcomes or facts of different observers in Wigner-Friend type of experiment have only meaning relative to observer-specific experimental setup, context, in agreement with Bohr's idea of complementarity. Now, do I have a minute or two, or? Okay. People in my group know that I change my mind constantly. And I don't see this as a weakness. I'm not committed to any of, strongly committed to any of the paths. I want to challenge my understanding and deepening this, but that doesn't mean that I don't make my choices, and I don't think that I need to follow all the paths. But one thing that intrigued me is something, and what I want to look at in future is the possibility of switching between the bubbles. And in a paper with Veronica first, in the Wigner's Friends as a Rational Agent, and more recently with Flavio and Gonzalo, we took this path, and I want to read you the abstract, and you will understand from the abstract what I mean. So here we show that the situation is more symmetrical than it's usually thought. There are different types of information that each of observers has that the other fundamentally cannot have. They reside in different bubbles, in Cavalcanti's terminology. While this can explain why the objectivity of the state assignment is only relative to the bubble, we consider a more elaborated situation in a form of a game in which the players can switch between bubbles. We find that in certain circumstances, observer may be entitled to adopt and verify the state assignment from another bubble if they condition their prediction on all information that is in principle available to them. And so, it's a practical question. If some extraterrestrial civilization just tell us, guys, you're just heading to the beam splitter, how should we act? And that's what we try to answer in this paper. And finally, I think the Wigner's Friend situation is not so uncommon. And it's common to all reasonable, universal, and probabilistic theories because these theories are probabilistic, just like quantum mechanics is. So that means that we need measurement apparatus, context, observer, to extract probabilities from a system. So there must be a division between subject and object, but it's a functional, not physical distinction. That's one part of the story. On the other hand, we want theories to be universal. Anything can be a system. Not everything, like Perez told us, but anything can be a system. So what was your measurement apparatus, Marek, maybe will not be my measurement apparatus. I will treat it as a system with respect to my measurement apparatus. So I do think you need measurement apparatus, but we don't need to agree on what they are. And I feel that any theory that is universal in that sense and probabilistic necessarily have a Wigner's Friend situation. It's a feature, not a bug. And finally, that's my final slide, probably I'm just confused. And I like to cite here Danny Greenberg. He said, I'm confused, therefore I am. So I hope that we just overlook something, or we are not mature enough to understand the thing. With this, I would like to thank you, and also I want to thank to all of my co-authors on the topic of Wigner's Friend. Thank you very much.
Thank you, Časlav, very much. We'll proceed with Eric and his presentation.
It's an honor to receive this award on behalf of all my co-authors. So first of all, let me acknowledge them: Kokwei Bong, Anibal Utreras-Alarcón, Farzad Ghafari, Yongchang Liang, Nora Tischler, myself, Jeff Pryde, and Howard Wiseman. Kokwei, Farzad, Nora, and Jeff were part of the experimental team on this paper. The other authors were part of the theory team. The two first joint co-authors, PhD students. Nora was the experimental corresponding author, and I was the theory corresponding author. And it's a special pleasure to be talking about this work on a conference celebrating the 60 years of Bell's theorem, because as I will discuss in more detail, this work opens a long-term research program which involves tests which have stronger significance than violations of Bell inequalities. The violations of LF inequalities would have stronger significance than Bell's in a way that I will discuss shortly. And I like to call this field, not me, I'm using Shimone's term, experimental metaphysics. I learned recently that it was his term itself, he didn't coin it, it was Michel Bessot, Einstein's friend. But he used it to describe the field that was essentially started by Bell with his theorem, where we realized there's certain hypotheses which can be seen to be metaphysical in that they don't lead to testable consequences, but also because they may be talking about things like reality and observation and our access to it, making a distinction between ontology and epistemology that generally in ordinary physics we don't. So for that reason I think the term metaphysics is accurate. But also it's experimental because we find that certain conjunctions of metaphysical hypotheses lead to experimental consequences that can be tested. And then you can rule out whole classes of theories in doing that. Not only is this science, but it was awarded the 2022 Nobel Prize in Physics, as you all know. So to relate to Bell's theorem, I'll remind you of the first talk of this conference from Reinhold Bertelmann, where he talked about his socks and how Bell used that to explain his notion of local causality. And Bell said, the philosopher in the street who has not suffered a course in quantum mechanics is quite unimpressed by PR correlations. He can point to many examples of similar correlations in everyday life. The case of Bertelmann's socks is often cited. When you see that the first sock is pink, you can be already sure that the second sock will not be pink. Observation of the first and experience of Bertelmann gives immediate information about the second. There's no accounting for tasters, but apart from that, there is no mystery here, and it's not the APR business just the same. So why is the philosopher on the street so unimpressed? They see a correlation between sock A and sock B, and they see, there's a very good explanation for this correlation. It calls for some explanation, but here's one. Bertelmann wakes up in the morning and he flips a mental coin in his brain, or let's just model it as an option between two different situations. If his coin, let's call it lambda, is 0, he puts the pink sock on foot A. If it's green, he puts the green sock on foot B. Otherwise, the reverse order, and I'd say that that's 50-50 probability. Of course, that's a rough model of what Bertelmann is actually doing, but that's the kind of explanation that one has in mind. And then important thing that is knowing this fact about the common cause, the correlations factorize, and you can recover the correlation by averaging over these hidden variables. Now, you can think of this reasoning as an instance of a principle from Hans Reichenbach, a philosopher who coined it, Reichenbach's principle of common cause, that if you see a correlation between two events, you seek some kind of causal explanation. And not only that, but you seek a causal explanation which will independently explain the events so that the probabilities for those events to occur factorize. Bell's notion of local causality is almost that, just with the added assumption that any causes of an event are in its past-like cone. So with those two together, you get local causality. And to get Bell's theorem, just need a couple more ingredients. First, of course, you have the choices X and Y for Alice and Bob. And you need to make an assumption that there is a single space-time out there where you can locate all of these events and talk about Lycons. And you assume that those events are single events. The events X, A, B, Y have been observed and they can be located in space-time, not, say, in different branches or undefined where they are. And apart from local causality, which follows from the other two assumptions that I already mentioned, we need some assumption that plays the role of the free choice assumption in Bell. So we can use this assumption that we call local agency. that a free choice is uncorrelated with events not in its future light cone. Then with that, you can derive the Bell locality condition, the factorization condition, which leads to Bell inequalities. Now, a common response to Bell's theorem, which is what you would have to do if you take the position that Bell's theorem implies a violation of realism, or implies that there are no hidden variables, or implies that outcome independence fails, but you can keep parameter independence. All those are instances of rejecting Reichenbach's principle of common cause. Now, one problem that you may think there, but then what about Bourbon socks? Why was the philosopher on the street, so quick to jump to the conclusion that that's the kind of explanation that you should be seeking? Does the world require that there must be an explanation of this kind? And how do we make sense of, say, the fact that these kinds of explanation work so well? And there's a whole book written by Julia Pearl, formulating this framework of classical causal models that's so applicable in many fields, and leaves a little bit of a puzzle of what do you do to make sense of that. Thinking about that question, in 2014 with Ray Lau, we suggested that we can break down Reichenbach's principle into two independent principles. One is the principle of common cause in self, which just says that correlations require some causal explanation. And the other is that what it means for a common cause to explain the correlations is that it factorizes the probabilities in the way that Reichenbach required. Let me also just define a notion of independent interventions, which is that an intervention is this free choice that you can make, can be made via external variables which have no relevant causes among the other variables that are relevant in your experiment. These now imply local agency, then those are sort of the errors in logical implication. And so, absolutes of observed events, local agency, and Reichenbach's principle imply Bell inequalities, which have been shown to be violated by nature quite conclusively now. Now, what do we do with that way of resolving Bell's theorem, which rejects Reichenbach's principle? One thing you can do is the proposal that we also did in that paper, following this framework of conditional quantum states by Matt Leifer and Rob Speckens. That there's something else that factorizes, which are the Choi operators from the common cause to Alice and Bob. So they can replace this idea of decorrelating explanation in Reichenbach's principle. And it's the kind of explanation that's been carried out to quite a bit of detail in this framework of quantum causal models, which I don't have time to explain here. So that's one way to make, to accommodate that kind of position. But one of the difficulties now is with this new no-go theorem that I'll discuss now, which uses Časlav's very great intuition about the possibility to prove a no-go theorem in this scenario, which involved two observers that we call Charlie and Debbie, and two super observers that, by assumption, can perform quantum operations on those labs called Alice and Bob. Okay, now in the way we normally present that, we say when x equals 1, Alice flips a coin. When x equals 1, she asks Charlie for his outcome. Otherwise, it may not be necessarily just two other choices, there may be three or more. She will do some other experiment. One particular experiment that she can do is reverse the unitary evolution that entangled Bob with the system. That's not the only way that she can do an experiment, and there's no particular assumption of the theorem, just one way of visualizing what's going on. And then she proceeds to measure the system itself directly. And we can locate those events in space-time according to this diagram. Then local friendliness is the assumption of absoluteness of observed events and local agency, and then we show that from these we can derive local friendliness inequalities, which are constraints on the observable probabilities, like Bell inequalities, and which can in principle be violated by quantum mechanics if this technological assumption holds that a super observer can perform arbitrary or close to arbitrary quantum operations on an observer. And we also do a proof of principle experiment, and I'll discuss a little bit more about that soon. So just very quickly, what the no-go theorem involves. The assumption of absoluteness of observed events is, as Časlav was mentioning, the assumption that there exists adjoint probability distributions for the events that are occurring in a given run. Not all the possible outcomes of observations that may be done, but in any particular run, the ones that are observed by some observer, which are C, D, X, Y, and B, the actual values in a particular run, such that you will recover the marginals, the empirical probabilities for Alice and Bob. By this setup, there is also an assumption that when X equals 1, the Alice's outcome is equal to that of Charlie, and similarly for Bob and Debbie, which is not directly following from absolutes of observed events, but has been called an assumption of tracking by David Schmidt, Matt Leifer, and Liang in a review paper. Local agency plays a similar role as the assumption of parameter independence, that's usually called parameter independence or locality in derivation of Bell inequalities, and the assumption of freedom of choice. And from these, they imply a local friendliness model which has a certain form, not exactly the same as just the factorizability condition of a Bell inequality, and from these we derive the local friendliness inequalities. Then these form a polytope like the Bell polytope, which is strictly contained in the local friendliness polytope. Here the Bell polytope is in green, and local friendliness in orange, and the purple in the no-signaling polytope, and the red is the boundary of quantum correlations. And then we show that, say, there are some points here which violate a Bell inequality but do not violate any local friendliness inequalities. There are some points in which quantum correlations violate both of them. And whenever a Bell inequality is violated, whenever an LF inequality is violated, a Bell inequality is violated. Any experiment that is an LF experiment is a Bell experiment. And so, meaning that the violations of LF inequalities have strictly stronger implications than violations of Bell inequalities. So let's think a little bit more about that. Some other results, these polytopes had been previously studied under the name of partially deterministic polytopes in a different context of device-independent randomness. And we recently generalized to most partite scenarios as well with my PhD student Mao and Hadra. And also we proved a possibilistic version of this no-go theorem, which then removes one of the possible objections, which is that about the use of classical probability in the proof. And we did a proof of principle experiment, and of course we call it proof of principle because the observer is a very simple observer, because it's the path that a photon is taking in a polarizing beam splitter. Marek would call it a pre-measurement. And asking the friend would just consist of measuring the path, and performing one of the other observations would consist in undoing that unitary evolution and performing a different measurement. Oops. We then show that we violate all of these Bell inequalities, and in particular say that some states in which that violate some Bell inequalities but no local friendliness inequalities, expressing how those are stronger conditions. Okay, now in comparing the two results, note now that those assumptions that correspond to this rejection of realism as usually thought of, and which can be made a little bit more interesting in these frameworks of quantum causal models, they cannot resolve this no-go theorem because those assumptions are not made in the derivation of the LF inequalities. And to make things worse, more recently in this paper with Liang and other co-authors, we showed that even non-classical causal models beyond quantum, if you allow some arbitrary GPT causal model, you cannot explain these correlations. And also there is a version of the no fine-tuning theorem for violations of Bell inequalities, that any non-classical causal model requires fine-tuning to explain correlations in an extended Wiegand's friend scenario. So the challenge is more complicated. To maintain compatibility with these causal assumptions that were the motivation for quantum causal models, to try to maintain compatibility with these causal assumptions that are motivated by relativity and with Leibniz's principle, it seems that we need perhaps more relativity, as Časlav was suggesting. Maybe events themselves must be relative. But that's a whole research program. Of course, there's interpretations like average that do that, but whether that can be done, or cubism, whether that can be done in other ways, it's an interesting question, how precisely to make sense of that. Now, of course, all of this is if these inequalities are violated in a way that is convincing. And that brings us to the question, what would that look like? What would be a convincing violation of the inequalities? And then it brings to the question of what is an observer or an observation? Now, what we can prove, what any experiment can prove, is that given some criterion, some candidate criterion for what an observation is, any experiment in which has a system that satisfies that criterion, either local friendliness is false, or that criterion is not a sufficient condition for something to be an observer. So that means we learned something with these experiments that have been done, that not all physical systems can be considered observer or local friendliness is false. We don't know that local friendliness is false from the experiment, but it's some information. We learned information about a disjunction. And it is possible that the experiment could fail for more complex observers. That's for nature to decide. So where do we go from there? What's some directions that we can go? Now, one of the possibilities, of course, is to just postulate that an observation, a measurement, requires an irreversible amplification. And that's untestable. And if that's the case, the experiment cannot be done by definition. It would mean that if one day we did an experiment with a human being, we would just have to declare that that was not an observation after all. Another direction that we can consider for experiments that could potentially be done, we can divide broadly into categories. One which look at quantitative measures of complexity or decoherence. When does decoherence happen? So you can give some sort of measure for how good decoherence has occurred, how irreversible, even though not completely irreversible, the system is. That's been done recently in a paper by Will Zhang and collaborators, looking at this branching factor in both simulations and experimental implementations in a quantum computer. Another would be some measure that would correlate with consciousness. We don't know what that is, but there's some candidate theories like IIT, Integrated Information Theory, that if anything, what they have going for them is that there's something that you can calculate and you can test. And again, you would test a conjunction, right, of that assumption together with local friendliness. More interesting, I think, and more qualitative measures, or not measures, qualitative criteria, are situations in which we start to be, to require talking about these systems as being observers, where a sort of an intentional stance, using Bennett's terminology, starts to become useful. Well, not the first case there, there's still a qualitative criterion, which is just a system that's macroscopic, only just in the sense that it's observable by the human eye. That's something that's not too hard to imagine. The human eye can detect perhaps 100 photons. It's challenging, but not so challenging that it seems impossible. But more interesting would be systems that that require some sort of intentional stance to describe the behavior. They have agency, or there are uses of quantum theory, and then it starts opening the question of if you have to encode, program the system with some probability rules, what probability rules would you use? Would just a Bond rule be enough? All the way to perhaps a community of speakers which share some sort of intersubjective agreements in reality which you can verify at least when opening the box, so to speak, all the way up to an artificial general intelligence. And for that last one in particular, we did some sort of very detailed calculations to some extent, considering an experiment in which you have to both encode this classical program as a reversible computation, consider all kinds of overheads, given the estimates for what the requirements would be for some human-level artificial intelligence. It's very challenging, extremely challenging, but not nearly as challenging as the numbers that we get if you think that what you're looking for is reversing some macroscopic object. I think that is just asking the wrong kind of question. And then finally on that, if that sounds just completely crazy to you, I would say never doubt the ingenuity of experimentalists. Hearing that from Anton Zardinger today. I think he was quoting someone else, but I think the sentiment still remains. Thank you.
Thank you, Eric, very much. We will now have Renato.
Okay. Thanks, everyone, for staying until the end of the conference. It's of course an honor to talk here, and I want to thank everyone who was already thanked by the other prize winners, but I also would like to actually thank the other prize winners to help making this topic of Wigner's friend more popular in the scientific community. I think it's an extremely important topic because it's a way, at least for theorists, I'm unfortunately not, I don't have this ingenuity that Anton has as an experimentalist, but as a theorist, to test the limits of our currently best known theories. So I put here the title of, or almost the title of the original paper for which the prize was given with Daniela Frauchiger, and I also wanted to thank her for her contributions at that time. So she left science, but she's still following the development here. Now, there has been a lot of follow-up work, and here on the slide you see the follow-up work that has been done in my group, and also some work that is going on. In particular, last one, so you see it's submitted in the future, and I will talk a little bit about that. So, if you look into the, let's say, question of Wigner's friend, as I just said, it's trying to explore the limits of quantum theory. But some people say it maybe goes a bit too far. We are now testing a theory by looking what happens if we now do some brain surgery essentially on a friend. So we have the friend in the lab, and at the end we carry out this measurement. So Časlav mentioned that this idea was introduced by Dakić, that we could not only have the friend in this isolated box, Wigner could later actually carry out a measurement on the friend in a superposition basis, which is probably a quite invasive thing to do. And one could say, okay, this is so artificial, maybe that's a bit problematic. But the question is, could we maybe do a Wigner's friend experiment without doing to Alice or to the friend any harm, or maybe almost no harm? Maybe we just have to push her slightly into a black hole, but otherwise she would be fine. So what I'm trying to tell you is that the experiments around Wigner's friend that we just heard about may actually be quite relevant in this larger context of testing quantum theory in connection to general relativity, and actually that thought experiments that have been proposed in the community that thinks about the compatibility between these two theories are in a sense also suffering problems that we see or that we have exposed in the Wigner's friend scenario. So that's somehow one of the goals here. Okay, so the question is, can we have a more natural setting in which we have something like these measurements on the friend? And you see, the setting will involve black holes, but this is a much more natural setting than having a perfectly isolated lab. Black holes at least exist. We have photographs of them, and they, in a sense, can replace possibly this thing of having measurements on perfectly isolated labs. So again, just to set the context, what is done in the, there's a big research community at the interface between quantum theory and gravity, and of course here in Vienna I don't have to tell people that Časlav is one of the leading forces in this area. And the big question is, how do these theories fit together? Do they even fit together, or are there some incompatibilities? I mean, we expect there are some incompatibilities, but the question is, what are they? What are really the conceptual issues when we try to combine the theories? Of course, there are technical issues, but I'm really more interested in the conceptual ones. So quantum theory has only been tested in a small realm. That's what is indicated here with a few spins. General relativity also has only been tested in a small realm. I mean, we have observed black holes and so on, but there's of course much more that could be tested. And in particular, we have currently no access to the intersection until maybe Markus Aspelmeier will be at the end of his big program and has done these experiments that bring these things together. Okay, so one of the thought experiments, so as I said, I'm not an experimentalist, so I return to thought experiments, and one of the, I think, really interesting thought experiments that try to test this regime is the black hole information paradox. There are many variants of this thought experiment, but the important point is that this thought experiment involves elements from quantum theory and from general relativity. And so I would now like to talk about some work of like understanding this thought experiment in a way that links it to Wigner's friend experiment. And this is this ongoing work in the future that I'm currently trying to finish in some way. I mean, I'm talking today about it together with Ladina Hausmann, who is also here. So in case you have questions, she may help answering them. Okay, so what is this black hole information paradox? I will now already kind of change it from the standard description in such a way that suggests a similarity to Wigner's friend experiment. So we start with two agents. One is Wigner, W, and the other one is Alice. You could also think it's the friend, but because there may be other friends, as you know in these extended Wigner's friend experiments, it's maybe good to give them more specific names. So Alice, we assume, has kind of a dilution refrigerator, that's this thing here, with some qubits inside, or some spin particles, which are entangled to some reference. So this reference here will stay outside for a long time. You can just think of this as carrying in, or Alice just starts with this entanglement, which is of course a standard thing in quantum information, that we say information carried by someone has to be about something else. So we have these entangled systems. So Alice and Wigner now continue with an experiment, which involves, as I said, Alice jumping into the black hole. So this little circle that you see should be the event horizon of the black hole, and Alice can cross it. And so you should think of this like the orders of magnitude, just to make this, in a sense, not too cruel. You can imagine this black hole is so big that the tidal forces at the event horizon are sufficiently small so that Alice doesn't feel much stress there, and she still could survive a few hours while being within the black hole if it's large enough. So I think this is, in a sense, realistic. There are black holes of that size. Now, you see this sequence of pictures. So in the first picture, Alice jumps into the black hole. In the second one, she's inside. And we know that as we cross, or if a freely falling observer crosses the event horizon, probably according to our current understanding of GR, nothing special happens. So they can continue doing experiments. And in particular, Alice could now do a measurement of the spins in the, let's say, set basis, or in the computational basis, and records the outcomes. So this is what is indicated by these little sets. She has these 4 spins and gets 4 values of the outcomes. Now, meanwhile, Wigner stayed outside. And I will now assume, and this is, of course, an assumption that is not commonly agreed on, that the black hole acts a bit like a mirror, in the sense which has been described more specifically by a famous paper by Patrick Hayden and John Preskill, that if you throw some information into the black hole, as they said it will be pretty immediately radiated out again by Hawking radiation. So here what you have to, by the way, keep in mind is that Hawking radiation is really an effect, or one of the few effects that is well understood, despite the fact that we don't have a theory of quantum gravity, because it's in a regime that is kind of accessible, but it's really a quantum gravity effect. It's an effect in the sense that it's involving gravity, and quantum field theory on curved space-time. And if you now want to argue that there is also information carried by the Hawking radiation, you need to assume that the black hole actually emits really energy to the outside and gets smaller, and that this energy could carry information. And so many in the community see this as a good model to assume that what will happen is that the radiation, so if you look at the whole process from the outside, from Wigner's viewpoint, it will look as if there was just a huge unitary going on. So there is Alice falling in, and then the radiation will just be some unitary evolution of the state of what fell in. So in this case of Alice together with her system. So this means that if Wigner now places an array of detectors around the black hole, he could just capture this radiation. So the radiation, by the way, will be mostly actually photons, you could imagine, depending on how we prepare the black holes. So this is something he could capture. And then he could, because everything is unitary, has in principle all the information of what fell in, he can now perform a measurement. And if he If Wigner performed a measurement in his computational basis, this would be a very complicated measurement in terms of, in a sense, the original basis of how Alice fell in, because there was this scrambling unitary of that made out of Alice the black hole radiation from Wigner's viewpoint. So anyway, we will assume that Wigner can collect this radiation and then carry out a measurement that will give him the same information as if Alice had carried out a measurement in the X basis. So that's a different basis than Alice used. So he just he captures everything, and so in particular he also gets, of course, the spins that fell in and can now perform a measurement on them. So Wigner now has information in the X basis about the spins. Now there's an important point in this consideration. You notice there are two agents that were involved, and you could ask, why did I even include two agents? We could just have a notebook falling in and no agent Alice, and maybe still say stuff like we can get the information from the notebook. But one important thing is that in general relativity, if we want to do the analysis, we have to first also choose an observer or a reference frame. And for example, if we take as a reference frame an outside observer like Wigner in this picture, this reference frame will just not cover the inside of the black hole. So in other words, in Wigner's description of what's going on, there is no inside. That's the whole point of an event horizon. There's just nothing behind that horizon from Wigner's viewpoint. But the event horizon is a subjective notion. It depends on the fact that Wigner stays outside. It's different for Alice who falls in. For a falling observer, there is another reference frame, another coordinate system, if you think in GR terms, and this coordinate system will cover the inside of the black hole as well. So we actually do two different analyses of the situation, one from Alice's viewpoint, which includes the inside. Ultimately, she will be there, and from Wigner's viewpoint, who will always stay outside. And in a sense, this is already comparable to when we talk about the Heisenberg cut in quantum theory. So what I mean here by the Heisenberg cut is we choose an agent has to choose what system he wants to describe. In this particular case, Wigner decides to stay outside and only describe the outside of the event horizon, whereas Alice decides to jump in, and with that has a different Heisenberg cut. She describes a system that includes the inside. But there are different regions that are captured. So the Heisenberg cut is kind of the cut around the system which we want to describe using our formalism, or our theory, in this case quantum theory, together with GR. So the next slide is the same slide, but it makes this more explicit, because this is really an important point. So the numbers now have colors, and the green color stands for this is just Alice's viewpoint. So from Alice's viewpoint, there is an inside. She can talk about the device she has, the dilution refrigerator with the spins inside, and she can talk about the measurement outcomes which are stored somewhere. So the first two pictures are from Alice's viewpoint. The second two pictures, 3 and 4, are from Wigner's viewpoint. And you see from Wigner's viewpoint, there is no Alice at the point once she fell inside. Of course, at the beginning, as long as she's outside, she still exists in Wigner's view, but afterwards, there's just Hawking radiation, but there is no Alice any longer. And nonetheless, he can, of course, now talk about this Hawking radiation and that he retrieves whatever would have been his spin qubits. So we have these two different so-called Heisenberg cuts in this gravity experiment. And this is, of course, very similar to how we think of Wigner's friend experiments. So we have the Heisenberg cut of the friend, which is, in this case, just, here this is now a different scenario. The friend is just in the usual Wigner's friend experiment in an isolated box and talks about the qubits or the spins, the 4 spins in the dilution fridge. And so his Heisenberg cut would be around that fridge, so it's somewhere like this. Conversely, Wigner's Heisenberg cut is such that it includes the whole isolated lab. That's how we think usually in the Wigner's friend scenario. So in that sense, there is an analogy in this conceptual sense. Now, at this point, both paradoxes, the Wigner's friend paradox and this black hole information paradox that I just described, are not really paradoxes in the sense that there is a contradiction. In the Wigner's friend paradox, this is just a standard Wigner's friend experiment. We could say Wigner never can talk to the friend, or if he does, then of course it destroys the superposition. So there's not really a contradiction. We have just two viewpoints, but they are never compared. Conversely, or similarly, in the black hole information paradox, we just have Alice, who is now inside of the black hole, and Wigner, who is outside, and they just describe different areas of the universe, if you like, so they can also not compare their views, and therefore there is not really a contradiction. And that's what people called the black hole complementarity. They're just two complementary views, and we shouldn't compare them, and that somehow resolves the issue in the sense that there's not really an operational contradiction. But that's, of course, not the end of the story. In particular, as you just heard from the other talks, we have this extended Wigner's friend experiment that turned this original scenario proposed by Wigner into something which is, I would say, in an operational sense, much more or leads to a contradiction, of course, still under certain assumptions, which I will come to. So the extended Wigner's friend experiment look like this. You have just seen them before. We usually have now not only one friend, but two friends in two isolated labs. In the version that I have developed together with Daniela Frauchiger, the two friends labs actually at some point exchange 1 qubit of information. This could also be done differently. There are equivalent descriptions. And there is also communication between the outside Wigners. And so at the end, one analyzes what the different agents, how they kind of think about the situation. But now that the scenario is arranged in such a way that they can really come to potential contradictions. So let me again return to the black hole information paradox and tell you what that would mean in that particular case. And that's even what is done. So that's not kind of a completely new thing. So what happens in the black hole information paradox? In the black hole information paradox, so far, we are at point 4, or at picture 4. Now, the next step would be that there is an additional agent we introduce, like in the extended Wigner's friend paradox. The blue one, let's call her Ursula. That will be a similar position as in the extended Wigner's friend paradoxes. She talks to Wigner, and then also, of course, then knows what Wigner's measurement outcomes are. And then she also jumps into the black hole in picture 6 and compares and just asks, she will meet Alice there. So the black hole really has to be big enough so that Alice can still be reached once Ursula jumps in and asks Alice what outcome she got. Now, Ursula is like a referee. She has now the two views. She could collect the two views, the view of Wigner and of Alice, and in that sense could potentially compare them. And now you already see this is a seemingly contradictory situation, because now we are in a, or let me explain again, by the way, before I come to the contradiction, that again one has to be careful about the viewpoint. So I now put blue numbers on the new two pictures, indicating that this is now the viewpoint of this third agent that I introduced, and this third agent is again a free-falling one, so this agent has a coordinate system that includes seeing Wigner and seeing Alice, but for example, this Ursula would never see the Hawking radiation. For a freely falling observer, there is no, or basically no Hawking radiation. You can at least arrange it in such a way that there is none for them. So Hawking radiation itself, the existence of the radiation is an observer-dependent effect. So we cannot just say Wigner now jumps in, because for Wigner the Hawking radiation existed. So we have this third party which is free-falling, and being free-falling means that you have a completely different view of is there radiation or not. So what one would appear as a fact, there is radiation or not, is just an observer-dependent thing in this scenario. So now, why is this a contradiction? So Ursula now has collected the information from Wigner and from Alice, and one was the measurement in the X basis, one in the Z basis. And we know from quantum theory this shouldn't be possible. We cannot know both the outcome of a measurement in the X basis and the Z basis, because usually we have to decide to do one of the two, but we cannot do both. And actually, we could even lead that to an operational contradiction. We could say there was this reference outside that was always there. So you see it here. Oops. This one. And so we could have even a force agent who is now testing, so even later the agent jumps in and says, please, Ursula, tell me what these outcomes are for the measurement, for the X and Z measurement, and then this new agent, the pink agent, could measure the spins and check whether the outcomes, the claims are indeed correct, because initially, you remember Alice's spins were perfectly entangled, or were assumed to be entangled with the reference. So this means they should get the same outcome. So if the pink agent now measures a spin where Alice said, or where Ursula said the X value is pointing in that direction, she should be able to confirm that. And that should not be possible. That would be kind of a certification that something like cloning happened, because we know we cannot predict both values at the same time. So we really arrive at a contradiction in this information paradox. And now I come to the central question, kind of, which I want to answer in a sense. What's actually the origin of this contradiction? So at the beginning I said the whole motivation for the black hole information paradox was to test the consistency of quantum theory and gravity. But the Wigner's friend experiments, which are very analogous to what I just said, they just test the consistency in the sense of quantum theory itself. So now one could wonder, as there is such a kind of striking analogy between the two scenarios, could it be that the contradiction arises not because of the combination of relativity and quantum theory, but just because quantum theory itself is already, in a sense, has its boundaries or limits, or has certain conceptual problems that we cannot resolve. So let's therefore go back again to two of the pictures I showed you before, two stages of the black hole information paradox. And these are important stages which are seemingly harmless. Namely, there was a stage when the new agent that I introduced, whom I called Ursula, was talking to Wigner and asking, what were your measurement outcomes? And Wigner would just tell him, these were my outcomes, these were the X values. And later, again, the same agent, Ursula, talked to Alice once in the black hole and asked Alice, what are the outcomes you got? And will also accept that these are the correct outcomes, that Alice tells him the truth. So he kind of accepts that it's correct what he's told. He's told something about the outcomes, about events in the language that we heard before, and just accepts that these events are also events with respect to him. And now, after the two previous talks, of course we know this is problematic. My way to say why it's problematic, and this is different in the different formulations of our Wigner friend experiments, is that it has to do with a kind of new test you can do for a theory. You can always test whether a theory is self-consistent in the sense that the theory is able to describe an agent who uses the same theory. So what I mean by that is, if you have an agent, the green one here, now you don't have to think of the information paradox, just take an agent like the green one who uses quantum theory to reason about an object. This could be a quantum object, a quantum book. Now, this agent uses quantum theory to reason about it and has therefore a mental picture or a formal, like quantum mechanical picture of what this is. Now imagine another agent, a blue one, who now reasons up. So this agent uses quantum theory, that's the important thing, to reason about how this agent uses quantum theory. That's referring to the original title of our paper. Quantum theory cannot consistently describe the use of itself. So here it's really, this person uses quantum theory to describe someone who uses quantum theory, and we want to remain consistent. So that's one assumption. The other assumption is now this one, and this is what we call consistency requirement. The consistency requirement is that if the blue agent here comes to the conclusion that the green agent came to a particular conclusion here in this little bubble, then if all agents are trustworthy in the sense they're just using the same theory, they agreed what is quantum theory and are all using that, then the blue agent can conclude that whatever the green agent concluded should also be true for him or her. So it's kind of a transitivity of knowledge. And this transitivity of knowledge was used in the black hole information paradox, because whenever agents talk to each other and take it for granted that whatever they are told is correct, they use that in a sense. So Now, the problem is that what was shown in our paper is that these two assumptions that we can reason using quantum theory with an arbitrary Heisenberg cut, so this means in particular we can reason about other agents who are using quantum theory, that's this assumption Q, together with this consistency assumption that I just mentioned or briefly explained, which one could say is kind of transactivity of knowledge or allows us to transfer knowledge. So in a sense, as you're listening to my talk, if you are not just hearing that as words but try to make sense of it, you're probably somehow using that assumption. These two things are incompatible in these extended Wigner-Friends experiments. So in other words, they are already problematic in quantum theory itself. And so this actually answers, in a sense, this question. We know that the assumptions that were used here in the black hole information paradox, if I take the same assumption, namely that information can be transferred from people who use different Heisenberg cuts to each other, this is clearly the case in this black hole information paradox, that this assumption, if you use it in a bare quantum context without any GR, already leads to contradictions. So that was what the theorem said. So in other words, we know the assumption that enter actually here are already problematic here. So in other words, we cannot conclude from the black hole information paradox that there's a problem in the connection between quantum theory and general relativity. The problem may already lie in quantum theory itself. Of course, together with this transfer of knowledge assumption, but you first has to replace it with something else, because if you don't replace it with something else, you can anyway not carry out this experiment here, so we need it. So that brings me to the conclusion. So the conclusion is, I showed at the beginning a slide where I had a question mark here at the inside, asking, are the two theories compatible? Now, what the Wigner-Friends experiment tells us is that the same assumptions that enter the black hole information paradox already lead to problems here. So maybe the black hole information paradox, the paradox or the contradiction that arises there is actually a pure quantum paradox. That's it. Thanks.